This time there is the optimization the presentation about optimization methods. That's more or less the highest level of using these computational tools, where you can combine the methods that you've seen for generating geometries or spatial configurations, how we often call it, with the analysis to evaluate how good it is. And then the third part is then this optimization, that you can ask your computer to find a spatial configuration that has a certain property in terms of the evaluation method that you can link with it. And then the system automatically rearranges the objects in order to achieve a certain goal that you defined as a planner. I will present you today the basics, how you can use Grasshopper for this task. There are two systems that I will show you. One is implemented directly in Grasshopper. It's called Galappagos, from the original developer David Rutten. He implemented this. And there is another one, a little bit more complex, called Octopus, where you can make more complicated, or where you can optimize more criteria at the same time. Right. To do this, I've provided you here the example files that we will need today. And there are two library files. One is the Octopus, that's this optimization system that we use in the second part. And the other one is the Clipper library, which computes Boolean intersections of shapes, which is helpful for today as well. And there is also this script in the folder. That's the fourth chapter about optimization, where I just described what we will do today, or what I will show you. So I will make the recording, and there is the script where you can look into it, and the presentation today. So this is hopefully good for you to understand the basic mechanisms for doing optimization. And in the end, there is the last task is, or the last exercises is that you just pick this up, the methods for optimization, and connect this to some model that maybe you have already done or what you have in mind for your project, and linking it with this optimization that you can generate and evaluate. So that's a kind of a loop, that you generate something, you evaluate it, and you change the configuration. We will see this later. So first of all, what we will do today, it's called Evolutionary Optimization. It's the kind of mimicry of the natural evolution, how biological species evolved over time. As you probably all know, there is the genetic information, the chromosomes, the genes that store the information how trees or humans or animals develop, grow over time, and this information somehow contains the instruction, or the genes contains the instruction how to grow a biological system. We will use this in a very, very simplified way. So we will have also genes, which are represented just as a box of numbers. That's more or less the simplest form of a gene, that you have parameters. And the parameters, they don't control a complex growth process like growing a tree. They just control the parameters of a parametric model. But if you imagine, if you can look for a combination of all these parameters, if you have to vary each with all the others to find or to explore all possibilities, then you have a lot of variance. And this optimization system is doing this for you in a more efficient way. So we will see this in the example later. But that's really to grow a solution, that you ask the system to optimize it for something, and then it automatically looks for the best combination of the parameters. To look into it, we will just have a look at the first example. That's an example that's provided in Grasshopper. Just showing you the interface, how it works. You see it in the example file. That's the box example, David Rutten, bounding box. It's the title of the group. And what you see there is basically a curve, this green curve over there. And around the curve there is the box, or a box. And the box is a minimal bounding box. And what you have here in these parameters, you can rotate the box in X and Y direction. And then it changes its volume. So you see here the volume is written in behind. And if you do it by hand, I mean, probably I provided you a file where it's already the best solution, but if you just move these sliders, then the question here is which parameter setting of X and Z rotation creates the minimal bounding box. Both sliders to 0. Then you see one slider is rotating it on one axis, this minimal bounding rectangle, or I mean you don't rotate the bounding rectangle, you rotate the plane. And there is the other slider for the other axis. And in the end it generates a different bounding box. And I mean that's a very, very simple example to demonstrate the mechanism of this optimization system. You have these two sliders. They represent a very simple chromosome. Means the information that's used to generate a geometry, in this case the bounding box around the curve. And you see here this component, that's this Galappagos component. This comes from the parameters and the utilities. There you find this Galappagos optimizer, and these two parameters, they will be varied, so the system will vary them systematically. And then you have the fitness function, and this comes from this value. So the volume is computed from the bounding box where this green line is connected, which means the optimization is taking these two sliders and the information about the volume of the generated bounding box, and it will try to minimize the volume. So we will see if we run it. The aim of the whole optimization is to find the bounding box with the minimal volume. And if you do it by hand, you can just play around with it. It's not trivial to find it. So the optimization, if you open this window, then you get a separate interface, the Galappagos editor. You have here the basic options of the evolutionary solver. There are two implemented. We will only look into the evolutionary solver, which is here. There you have these basic mechanisms, or basic parameters. The population means how many variants or individuals, how it's called in this in the methodology, do you have. And this means, for example, 50. In the first iteration, it generates 50 random combinations of these two parameters. So just 50 values of X, 50 values of Z. And you generate inbreeding 75% of children. This means you take these two so-called you take the parent chromosomes. In our case, it's just two values, and then you mix them with another parent. So, for example, taking value from this parent and mixing it with the other value from the other parent, and then you have made a crossover. So that's the simplest way of combining two individuals, just mixing their parameters. And then there is also a mutation probability that randomly changes these values a little bit. And if you go to the solver, here you see this evolutionary solver. The other one works works similar. And if you start it, you see the bounding box is moving around more or less randomly. Not randomly, but it shows the best solution that's found during this process. In the beginning, you see you start with just randomly generated variants, and then over time it tries to in the next generation it uses only the best individuals that are generated, and so it improves it over time by doing these operations that I've explained, making crossover mutations, and then you have the next generation of parents, and from these parents you generate again the childs by doing crossover, mutation, and so on. This diagram just shows you the best individual and the average quality, in our case the average volume of the 50 parent chromosomes, and then the distribution around it. So if there's the average, then you have the better ones and the worse ones, and it's continuously searching for better solutions. I mean, now it's stopped. And I think that's already a good, so that's a simple problem, and it already finds a good solution very soon. Here you just see some information about the distribution of the best parents and how far away the children are generated from it. So that's the pool of solutions that you have. Here you see only one solution, the best solution. Here you see how many exists in the background or after every iteration. So that's more or less a visualization. It's difficult to explain the detailed meaning. Here you see the chromosomes itself, means the quality, the volume that's generated over time. So that's our best one. The second best one has then 581 cubic centimeter and so on and so on. That's then this distribution. So that's the rough mechanism. There is also a very nice website from David Rutten where he explained all the mechanisms in more detail. That's what I linked here, this Introduction to Evolutionary Optimization, maintenance mode, I'm sorry. Ist das nicht Moodle? Moodle itself is in maintenance mode. That's bad. Anyway, I hope it will work soon again. And then there is the link where you have an introduction where it's explained in more detail how these evolutionary mechanisms work with having parents, creating children from them, making mutations, crossover, and generating this pool in terms of searching for a best solution. But what you need to use it is the understanding that you have chromosomes, means parameters, and you need objective or fitness functions that determines the quality of a solution, and the system will minimize the fitness value. So in this case, our volume will be minimized. If you want to maximize something, you just have to divide it by 1. Then it's turned around. So it doesn't matter if it's the real value or a very small value, it will always look for the smallest value, although independent how big the number is. Is it clear how to apply the evolutionary mechanism? So I don't want to explain you all the details of the theory of these algorithms. In the end, it's only important that you get an idea how you can use it. There I provided you something more related to our context. So if we turn this off. It's not really complex, but is the distribution of rectangles, which you can interpret as buildings on a site, and they are controlled with this chromosome here. Here you see, instead of having a lot of individual sliders, which is a lot of work to create them, there is also the component gene pool, which you can find here again. And this provides you a set of sliders that are put together in one box, and there you can adjust how many you want to create, their maximum and minimum values, and if they are float or integer, and so on. That's very helpful for providing the basic information for this optimization process. If you click on this box, you can find with the right mouse button the Randomize 100% setting. That's important if you start an optimization. Ensure that you randomized it. Otherwise, if you test it, you will not see anything because it is already optimized from your last optimization run. And I think I provided you a file with an already optimized setting of these rectangles. So just do this randomization, then you will see something if you run the optimization. The problem that the components may have a red flag is that I use in the code an external library, this Clipper library, and you can use any library, means any DLL, in your C# script from the outside. In my case, it's this clipperlib, and if you want to edit that it appears there, you have to go with the right mouse button on your component, and there you find Manage Assemblies over there. If you click on this Manage Assemblies, it opens this reference assemblies window, and probably you don't have anything here. Then you can add a DLL, and if you have, so that's what I provided you in the download. I hope so. So you will find it in your installed clipperlib. Yeah, here you find this DLL, and you just have to link this, that it appears in this window. Right, so what you do with these, with the chromosomes, is that we have now to map the genotype, how this, how you can call this box of, how is it called, this gene pool, to map this information, because you see these are sliders between 0 and 1. And they control the position of these rectangles. So if you move a slider, and then you see this is the y, and that's the x coordinate of one of these rectangles. And they are controlled in a way that if you have 0, then it's at the bottom, and if it's 1, it's at the top. And this will work for every rectangle. So it will adapt the position to the minimum and maximum value inside of this rectangle. That we ensure that we distribute the rectangles only inside of our bounding rectangle. That's controlled by this C# script, which is very simple. You read the list of genes, which is a list of double values, and then you just have to somehow define on your own that you combine these values in a way that the first one is the x, and the second the y coordinate of the first rectangle, and then the third and fourth the x and y coordinate of the second rectangle, and so on. So what you do with these values, that's up to you for what you use it, what you control with them, what kind of parameters for which geometry they are. Here you are completely open. These are just values to control your parametric model. In my case, my parametric model is a model where I control the positions of the rectangles with these genes. In the code, we read the list of genes, means the double values. Then we also need the bounding rectangle, the bounding curve that we will use to compute the values for x and y based on our 0 and 1 range in the gene pool. So here you see you just get the bounding rectangle and you compute the bounding box of this rectangle, and from the bounding box you get the width and the height of the box. Because the width and the height is used, if you have a 0, then you know it's on the left side, and if you have a 1 for the x coordinate, you know it's on the right side inside this bounding box. Therefore, we will have also the minimum and maximum values that we compute for our coordinates, and the rectangles created inside this bounding box by using these with the values of the gene. Where do we do this? Here you use the value of the gene and you multiply it. So if your box has 10 units in the width and you have, let's say you have the value 1 in your gene, then you multiply the possible width. You have the value 0.1 in your genes, because you only can have values between 0 and 1. Means 10 multiplied by 0.1 is 1. This is then the coordinate of your rectangle. And this ensures that it's always inside the range of the width of this rectangle. So that's done in this script. You subtract also the half of the width of the rectangle itself to ensure that it's not so that the center plus half of the height or width is not over the rectangle. So if you look into it, this shouldn't be difficult to understand. So that's something you have done already in the other examples where we created rectangles and placed them based on center points and generated the top left and bottom right point for the rectangles. And then they are generated in a way that you already know, and you add them to the list of rectangles that you send to the output. And that's it. So that's my mapping function to translate the gene pool into a geometry. It's called mapping because somehow you map the abstract numbers to a geometry. And how you do this, you can do this in this very simple way, but you can also have a very complex algorithm or also a Grasshopper definition that translates these values into something. Okay, so at the bottom, that's just for visualization, that we can see these boxes as surfaces. So we don't have to care about this. The aim of our small script here is that we generate a distribution of these rectangles, that we ensure that they have a certain distance from each other, and that what we don't have in any case is that they overlap. So this should never happen, this overlap, and we want to control how far away they are from each other. Therefore, you find these components, these are also C# scripts. We start with this distance measure. So here we defined that they should have the distance of 0 between each other, means they should be very close to each other. You can also have other distance values, but let's start with 0. Means in the end we want to, you can formulate objective values that are not possible, because it's not possible that all of them have the distance of 0 to each other and no overlappings. That's difficult to find, or it's impossible that they are somehow arranged in this way because there are too many. But you can formulate it as an objective value, and the system will try to find something that's as good as possible. So first of all, we need to measure the distances between these rectangles. I've done this in the C# script, where I just compared, so you can compute the points if you want to compare the distance between these two rectangles. You can also visualize it. Which one do we choose? So here, for example, then Grasshopper computes you 2 points on these edges that are close to each other. Sorry, too many windows. So that's this point on curve and point on other curve that we let compute by this closest points function, where you put in one curve and the other curve over. So one curve, other curve, and then you will get back these 2 points. And then you draw a line, respectively, you compute the distance between 2 points. That's then your current distance. That's the distance between 2 rectangles. And then you compute the difference between the existing distance and the distance you want to have. So in my case, I have the distance 0, but if you say you have the distance 10, and if your current distance would be 9, then you would have 10 minus 1. The difference would be 1. 10 minus 9, the difference would be 1. And with this absolute, this math apps computes you always the absolute difference between 2 values, and then you sum up all differences of distances that you want to have. In my case, I want to have the same distance value between all rectangles, just for the case of a simple example. So that's the first, our first objective that we compute, or our first evaluation that we compute. Here we just return the sum of all distances, because the sum of all distances, that's what we want to minimize. Now we computed the length of all distances, and in the end we would have, we want to have a 0. But it's difficult again to find a combination manually where you place these rectangles in order to minimize their distances to each other. What we want to do at the same time, that's probably not working with your with the problem of this Rhino Common DLL, is that we compute the intersection, so the Boolean intersection. That's what this component is doing. We can do the same thing in a script, that we add all the rectangles and then we compute the Boolean intersection between these rectangles. Means we get the, I'll show you how this looks. So here, for example, I have a set of rectangles, and these intersections computes then these green areas where they intersect with each other. And that's the sum of these rectangles we want to minimize, so we don't want to have any intersection between these rectangles. That's done in the script. So basically it's one line of code that you really need. The other is just translating the input to the right values for this function. And this polyline, this clip type, we've defined. Where do we have it? Clip type. So here we say it's clip type intersection. Means we want to compute the intersection. And then we put in, so you can also put in lists of rectangles, and then it computes the intersection between all elements in your list. And for these intersection rectangles, we compute the total area. So that's this area mass property, what you can also use as a component. And then you have the sum of all these areas. So now we have two values, the length between all rectangles and the surface of all overlapping rectangles. That was my example here. So the length of all the lines and the sum of all the overlaps. What I also do here, that's not needed for now, I check the intersection of the rectangles with the bounding box, because we can also have a non-convex bounding box, and then it's not possible, so then we create a minimal bounding rectangle, but the rectangles could be here, and then there would be an intersection also with the outline, and you can minimize this as well. Therefore, this range of components is added, but at the moment, if you look at the result, it should be 2000. Interestingly, it generates something, but in the end, it shouldn't create anything. Anyway, what we do is now we put together the distances. We can also deactivate this. The distances and the sum of the overlaps into this mass addition, and then we have one value, and this value shall be minimized. So that's our fitness value. That's the fitness value, and that's these two functions are the fitness functions that you use to evaluate your layout. And now we can try what happens if we open this optimization. So that's the same way as we've done it in before. Here you see the result of our mass addition is linked to the fitness value. So that's a special way of linking the parameters to others. That's why they are green and red, because usually you send the information in the other direction. So here you say the fitness value is this value, and the genome, you can also link this either to individual sliders or, in my case, to this box, to the gene pool. And if we run it, you will see it will automatically rearrange our rectangles in a way that it's now trying to find a configuration where the distances are minimized and the overlaps are minimized as well. But that's a more difficult problem than rotating the X and Y, or to manipulate X and Y for rotating the bounding box. So here you see, obviously, always if it makes a new arrangement, there may be some overlap. So it's very hard for the system to find a minimal distance between these rectangles, because now we mix up two fitness values. One is the overlap and the other one is the distance value. And as you know, the distance is a one-dimensional measure. The area is a two-dimensional value, so it means if you have an intersection, you will have a much higher value because it's squared of two numbers. And if you have the distance value, that's a one-dimensional value, that's always smaller. That's why you can also weight the importance of these different fitness values. So if you say this one should be 1000 times more important than my intersections, then the system, so weight, you can just enter manually here a value with the right mouse button under set data item to something you want to test. So far what you have seen is a single optimization method with this Galappagos. Means also if you have more than one fitness values, like the distance and the overlapping, you have to sum up somehow these values. You can have individual weights, which one is more important, means which one has a bigger proportion in the final value, which is this resulting value from our addition here. And that's then used for the fitness value. What you can do as well is that you use these values individually and you ask your system to optimize each of the values separately, which is then called the multi-criteria optimization, which is much more complicated because then you, if these criteria contradict to each other, so if you cannot find a solution where you can fulfill both at the same time, then you will create a so-called Pareto curve. We will see how it just looks. Means you have a curve of good compromises that are more or less equally good, but some is better in this and some better in the other criteria, and then you have a kind of curve that collects all good compromises. We will see this in this Octopus component where we'll do this. For using this Octopus, what I've done is I've added a more complex evaluation for our spatial configuration, because so far this was a more or less boring example with distances and overlappings. That's not really exciting. More exciting is if you use, for example, this view field analysis that you know from the urban analysis course. So down here you see these components for computing an isoist field. I think you know this already from SWAM very well. Yeah. So should be clear how it works. So you use these rectangles and the bounding rectangle as obstacles. Then you compute the isoist field and you get some properties out of the field, for example the area, so how much you can see from one point, or the compactness of the spaces, or this min radial property. And you can use now these properties as fitness values, and the C# script here, so until the output, it should be clear how it works. So you get these isoist properties, and then you have this list where you can define what property you want to return. And for example, I use the area value and put it into the script where I just compute the maximum value of this list, what you can do with another component as well. And this is then used as a fitness value for my objective function. In order to use a value as a fitness value for Octopus, you have to use this number component. So you just have to use the link the output parameter to a number component, because only this can be linked to the objective input of the Octopus over here. So now I use the isoist property area and this mass addition that doesn't work from our computation so far. Means I want to have a certain distance between the elements and they should not overlap. Plus I want to minimize the maximum area value. So in this case there shouldn't be a central place. The elements should be distributed equally. That's probably the outcome if I want to minimize the maximum value of my area values in the isoist field. And here you see you can link more than one fitness values. You can link the distance overlaps, what we have used here as well. And you have a second objective. This is not possible in the Octopus, in the Galappagos optimizer. Here you can only have one. Here you can have as many as you like. But don't use too many, because in the end, I will show you how it, if you double click on this component, it opens a different interface. That's this Octopus optimizer. There you have an interface where you see the solution, the quality of a solution. So you have here this small icon where you can rotate your solution, or you do it here with the right mouse button. You can rotate this view. And with pressing Shift and right mouse button, you can pan the view. And these two axes, they show you now the objective values. So each solution has now two objectives, two values for the two objectives. So an individual configuration that we create here has now a value for the summed distance and overlap, and the value for the maximum isovis property. These are the points in this diagram. Every point represents an individual configuration. You can also click on one of these points and say reinstate solution. Then you see what geometry corresponds to this point in your search space. And the Pareto curve, that's now the curve that you see here with the red dots. These are the best solutions found so far, concerning both criteria at the same time. Means if you say I want to optimize both values, this overlap and distance value, and the minimization of the area values. This obviously, so here would be a solution that fulfills both criteria at the same time in the perfect way. This is then 0 for both criteria, but this hasn't been found so far. So it means you can only click on the individual solutions showing the compromises. But probably in your solution there is nothing, because, or maybe I've stored it for you. Anyway, usually you start without any solution. And if you press, so here you see the settings again, for example, population size. I've made a smaller one, otherwise you will have to wait for a long time. By the way, if you use this isovis computation, if you have a graphics card that works for it, you can use the GPU computation, then it's approximately 10 times faster compared to the CPU computation. And this really matters in these optimization processes. Okay, but if you press start, then you see it turns off the whole Rhino window. And in the background, the optimization is running. And it continuously adds solutions to this solution space, and it always computes for you this new Pareto curve, showing the best found compromise solutions that you have so far. Unfortunately, you cannot see it during the optimization process, because that's really it uses all the resources that it can get, because you see in the background you have run so many evaluations so far, and you have to take care that you don't make very complex evaluations. Then you have to wait forever, because you evaluate many hundreds and thousands individuals. If you increase the population size, which you need to make a really meaningful optimization, then this lasts a long time. But you see it fills up over time with many, many variants, so the system tries to find better solutions, and so you get more and more points, and from time to time the line jumps towards the optimal point. But all these solutions are the Pareto optimal solutions. And then you can look through the generated solutions by clicking with the left mouse button on one of these elements, and then you will see the configurations. You see here also the gap that's caused by the creation of the isovist field itself. Sometimes the system uses only partial fields, but in general it works well. So that's a very nice way how you can use these evaluations coming from the computational urban analysis course, linking them with some methods for generating spatial configurations or geometrical solutions, may it be the arrangements of buildings. You can also have it in a three-dimensional way and measuring solar gains on your facade or shadowing of the areas. And all these measures you can take and, for example, compute the average of the solar gains or the maximum or the minimum values and use them as fitness values for an optimization process. And what's changed during the optimization is controlled by the mapping of your parameter values to some parametric model. There you are absolutely free what you choose. And then if you don't have these errors in your definition, you can do this with the C# script, but you can also compute everything with existing components. In the end, this doesn't matter. Unfortunately, the intersection, if this example hasn't worked, what I have not known. But usually, if you use working components, the process should run stable. Right. Is there any question so far? I mean, unfortunately, you couldn't follow with the code, but at least the principle should be clear. I've described also the main process here in the script, where you see all the code and the description, what happens in the code. Also with if you use more complex shapes, but in the end these are just examples to explain you how the general idea of this optimization process works. You don't need this intersection component at all. And here that's the theory of this Pareto curve. So each of these solutions is on the curve because the solutions in behind. So here this means you cannot find a solution that's better in both criteria. So this one is better in the criteria of this axis because it's smaller in F2, but it's worse in F1 because it's not down there. So this one is always better, at least in one criteria, than all the other solutions that you can find, because here the ones behind the Pareto curve, they are always worse in both criteria. For example, this one is better in both criteria than this one, so therefore it's not on the Pareto curve. Solutions on the curve, these are always the best compromises concerning one criteria of the two that they have. And you will, I mean, if you have a problem where you can find a solution that's perfect in both criteria, then you will end up here. You don't need the Pareto curve at all. But usually in urban design, urban planning, you can formulate kind of a wish list, what you want to be optimized, and you don't care about if it's possible or not. And then the system tries to find either an optimal solution or the best compromises. You can do this with two fitness functions with 2 objective values, as we have done it here. You can do it also with 3 or 4 or 5, but we can look into it, how this will look like. So here you see it's on a 2-dimensional plane where all the solutions are mapped. We can do this also if we take a third one. Which one do we take? For example, if you use the second parameter, the compactness value, and you say you want to minimize the maximum value of the compactness, then we have to add this to the objectives as well. So now you see we have 3 green lines. And if you look now into this Octopus optimization, you see here 3 values that are listed. These distance overlap values, the isovisc properties 1 and 2 means the area and the compactness. And if I reset everything, now we can look also in 3D and start it. Then we will not get a 2-dimensional Pareto curve, we will have a 3-dimensional Pareto surface. Where can I see this? So here you can view it with this Delaunay mesh. Rotate here. So here it already becomes difficult to imagine what happens, but all the possible compromises are of course not on a 2-dimensional curve anymore, because you have 3 dimensions. So you have many, many more possible compromise solutions for 3 dimensions. And this increases in terms of dimensions if you have more objective values. But it's difficult to imagine how it looks like, because we can only somehow think in 3 dimensions in maximum. 4 dimensions difficult to visualize. But the search time will increase exponentially, because here you have to search for the volume, the sphere, the surface, instead of just a 2-dimensional curve. So it's more time needed, and the probability that you really find an optimum or a good solution gets smaller, because these search bases becomes really incredibly large. So you won't find any meaningful solutions if it's too complicated. But in theory you can use as many criteria if you want. In practice you just have to test if it's really working. But the principle is the same. If you stop it, you can select one of these elements, reinstate it. But I hope you got the idea. You can, with this multi-criteria optimization, you can experiment with many criteria, and then you can just test what happens if you want to optimize it. So now I've used the CPU that's much slower than with the faster CPU computation of my isovisc field. So here that's of course a disadvantage with these complex evaluations. You have to wait forever until you get a good set of solutions. Okay, so here also in the script, the Octopus interface is explained a little bit, or at least the most important aspects that you need to know with this Pareto curve and all the dots and how you can switch between solutions. You see the setup to link these number components to the input, and that's it with the optimization. Is it clear how to use these components, or do you have any specific question that you have not understood so far, at least in using the components and somehow linking parameters, map the parameters to a geometry and then change the parameters systematically? I mean, of course, it also depends on how many of these control parameters you use. If you only have one control parameter, then it's simple for the system to vary it, then you can just do it by your own and find the best one. And the more of these parameters that you have, the bigger the search space becomes. So search space means all possible combinations of values that you allow the system to explore. You can also say you only want to have somehow steps that it's allowed only to use, so not the 2 digits behind the separator, but that you say you have 10 possible positions in the x and y coordinate for these boxes. This may be enough in a grid. Then the search space becomes smaller. So it's a good idea to reduce the number of possibilities to reduce the computing time. But the rest is clear, or not at all, so you don't have questions either because of the one or the other situation. Okay. So I just wanted to show you this because that's somehow the starting point really to use the power of automatization, of computing, in order to replace or to really to help you finding solutions that you cannot create easily on your own. Because with this optimization you can make a general model, what you want to consider in terms of how the solution should like approximately. In this case I've defined that I want to have so and so many boxes with certain sizes. We could also manipulate the sizes, for example the width and the height of the rectangles could be also parameterized. The height, if we would compute shadowing or whatever. So you can be very creative what you represent with the algorithm, and then what you measure. So now you learn to use a lot of measures in the urban analysis course. In this case you can apply it now. And then really the power is now that the system automatically generates something for you that you have not explicitly modeled. So the exercise would be that you just take these this mechanism of the optimization, you make a mapping function either by a C# script or by something else. In the end you need to translate a set of numbers to some kind of geometry, then you apply some measures, and then you run the optimization. Ideally, you can link it to a task that you have in mind for your design project. Maybe you can make a small experiment how you could apply it, or you link it to some of the exercises you have done so far with generating some spatial structures. I think most of you have already made some grids or some arrangements of elements that you can now manipulate with this kind of optimization. Otherwise, I would finish it for today with the input from my side and give you the time for preparing all the rest that you have to do. So thanks for being here in the small room today, and see you soon. Thanks.